Namaste and welcome to this course on the mathematical foundations of machine learning. We have been looking at the idea of vector spaces, vectors and subspaces and stuff. We looked at all that in the last class, and when we were about to end the last lecture, we had two questions in our mind. We had two questions, one which said, look, what happens if we add multiple vectors in a vector space? That means what is it to say combining the vectors? And second thing is, like, we had this analogy. We said that, look, suppose if I have developed a new vaccine and I want to give this vaccine to the entire population, like, is it fine that I give it directly to everybody, or how do I basically, what is the strategy that I need to adopt to study the effect of this vaccine on everybody the entire population. So how do we in the same level, what we are going to do is, or along the same lines, we are going to ask this question: suppose I want to transform the entire vector space, like, what is the strategy that I would adopt to study the effect of this transformation on the vector space. So these were the two questions that we posed at the end, towards the end of the last lecture, and we are now in the process of answering this question. To answer these two questions, we get into a couple of new ideas. So that is what we are going to look at in this particular lecture. We are going to look at the notion of linear combinations of vectors, and we are also going to look at what we call as linear independence and linear dependence of vectors. So that will be the focus of this class. Okay, so let us go ahead. So we had this question. So what is it to say combining vectors? So let us look at linear combination of vectors. Linear combination of, let us say, vectors. We have already seen that in the case of vector space, the two operations that are permitted are basically your scalar multiplication and vector addition. Now what are we going to do is, in this case I am going to look at adding scalar multiples of vectors and see what is it that I am going to get. So I am going to look at the following. So suppose, let us say u1, u2, etc., un are n, let us say, okay, let me just make a small change here. Let me call this as uk, u1, u2, uk are, let us say, k vectors with n components each, with n components each. That means I am going to have u1 to be u11, u12, etc., u1n, n components each. So what does that mean? This simply implies the vector ui is given by u1, ui1, ui2, etc., uin for I is equal to 1, 2, etc., k. So I have k n component vectors. Now what I am going to do is, I am going to take k scalars. I am going to look at k scalars. So let us say alpha 1, alpha 2, etc., alpha k be scalars. Now what are we going to do is, suppose we say that the vectors are all real vectors, we are also going to consider the scalars to be real. So assume that, so let us say n components u1 k vectors, let us say, defined over real field. Therefore I am going to have alpha 1, alpha 2, alpha k be scalar. So let us say this ui for I is equal to 1 to k are real vectors. That means the components are all real numbers, and let us say alpha I is equal to 1 to k are real scalars. Okay. Now what I am going to do is, I am going to define something. I am going to say that, look, the vector, I am going to define a new vector say V, which is going to be this way, alpha 1 u 1 plus alpha 2 u 2 plus etcetera plus alpha k u k. The vector V, which is obtained as the by adding the scalar multiples of the vectors u 1 u 2 u k, the vector V is called the linear combination, is called the linear combinations of the vectors of the k vectors u 1 u 2 etcetera u k. So, we are going to call this as the linear combination. That means what? We are just going to take some scalars alpha 1, alpha 2, alpha k, and then we are going to scale each of those vectors u 1, u 2, u k by these alphas, and then we are going to add them. So, the resultant vector that you would get, that would also be an n component vector, say V would also be an n component vector, which is given by the combining the scalar multiples of these vectors u 1 to u k, and that is precisely what you would call as linear combinations of the vectors u 1 to u k. So, V can be expressed as a linear combination of the vectors u 1 to u k. I mean, have we studied something like this before? Have we looked at something like this before? Of course, yes. We will just look at a simple some simple examples here. Let us see that. For suppose we have let us say u 1, u 2 etcetera u k are the what we call as the standard unit vectors, are the standard unit vectors. Now, what do we mean by standard unit vectors? That means we are going to have this u 1 takes the value, the first component alone is 1, the rest of the n minus 1 components are 0, u 2 is the second component alone is 1, the rest of the other components are 0 etcetera. u k has, let us say, the kth component is equal to 1 and the rest of the components to be equal to 0. So, this I will take it as the kth component. A very specific example, if you want to take, we can actually write this. We can say, suppose u 1 is equal to the two component standard vectors, unit vectors in 2D. I am going to take u 1 to be equal to 1 0 and u 2 to be equal to 0 1. Now, what I am going to do is we are going to say this, the vector V, which is equal to V 1 V 2 is a linear combination of these two vectors. So, I want to look at alpha 1 u 1 plus alpha 2 u 2. I want to write this V as a linear combination of alpha u 1 and u 2, where alpha 1 and alpha 2 are scalars. We would see that this is equal to V 1 into 1 0 plus V 2 into 0 1. So, this is basically the linear combination. The vector V is basically a linear combination. Best simple example would show us that. For example, we take 3 comma 4, the vector 3 comma 4 is nothing but the 3 times the 1 0 vector plus 4 times the 0 1 vector. So, this is basically a linear combination of the two standard unit vectors. The vector 3 4 is the linear combination of the standard unit vectors in R 2, right. Let us take another example. Let us probably look at this. Suppose we have this, alpha 1 is equal to alpha 2 is equal to etcetera is equal to alpha k is all equal to 1. All the coefficients are 1, in which case what I am going to have is I am going to have this vector V, which is nothing but 1 time u 1, say alpha 1 u 1 plus alpha 2 u 2 plus alpha k u k implies if alpha 1 is equal to 1, alpha 2 is 1, alpha k is 1, then I am going to have 1 u 1 plus 1 u 2 plus etcetera 1 u k. So, which implies V is nothing but simply the sum of the vectors, the sum of the vectors. So, V is nothing but the simple sum of the vectors u 1 plus u 2 plus etcetera plus u k. So, this is nothing but the sum of the vectors. So, we are just going to say that this is. So, V is the sum of the vectors. Right. Again we can look at an example. We say that suppose u 1 is this vector, let us say 2 1 and u 2 is the vector, let us say 1 2, then V is equal to 1 time u 1 plus 1 time u 2 is nothing but 1 into 2 1 plus 1 into 1 2, which gives me 3 3, right. This is what we have, and it is very clearly, I mean if you look at geometrically how this works, this is pretty straightforward. So, I am going to have this, I am going to have, let us say this is the just take this. This is basically the unit vector that I am having. Okay, let me draw it this way. Okay, sorry. So, I have my unit vector which is 1 0 and then along the x axis, and I have the other unit vector which is basically this along the y axis. Now, what it says is I want to find out what is u 1 plus u 2. This is, let us say this is the vector u 1 and this is the vector u 2. Now, we know how to add these two vectors. What you do is you bring this u 2 vector, the tail of u 2 vector to be at the head of u 1 vector, or you move this u 1 vector at the head of u 2 vector. So, the resultant is going to be this u 1 plus u 2 vector. So, the resultant is going to be this vector which is nothing but u 1 plus u 2, simple diagonal of the parallelogram that you are going to get, right. So, this is going to be my u 1 plus u 2 vector. Do we have any other interesting combinations? Of course, we have a lot of them, but then we are just going to take one more and then see what is the combination that we are going to get. So, suppose I have this, we have let us say u 1, u 2 etcetera u n, all n component vectors and we are going to consider again, let us say let alpha 1, alpha 2 etcetera alpha n be scalars such that alpha 1 is equal to alpha 2 is equal to etcetera is equal to alpha n is equal to 1 by n. We have 1 by n, in which case I am going to look at this vector V, which is going to be expressed as alpha 1 u 1 plus alpha 2 u 2 plus etcetera plus alpha n u n, which is nothing but 1 by n into u 1 plus 1 by n into u 2 plus etcetera plus 1 by n into u n, which is nothing but 1 by n into u 1 plus u 2 plus etcetera plus u n. Now, what are we seeing here? We say u is n component vector, u 1 is n component vector, u 2 is n component vector and u n is n component vector. I am going to add n elements and then divide it by n. So, this is basically what we are going to call as the average vector, right. This is going to be the average of the vectors. Average of the vector. So, this is something interesting. So, we would see this average of the vectors to be a linear combination of the vectors with equal weight, which is basically say 1 by n, suppose you have n vectors, right. We also have what would you call, suppose if we have this in this case, if you see, if you add up all the scalars alpha 1, alpha 2, alpha n, where alpha 1 is 1 by n, the scalars will add up to 1, and so when the coefficients sum to 1, you have a name for this combination, you call this combination as the affine combination. So, we are going to give a name for this, we are going to say that if the coefficients or the scalars add up to 1, we call such combinations as affine combination. We call such combinations as the affine combination. We have another interesting idea that comes into picture, which we typically look at, basically the idea of convex combination. We are going to make the statement, we are going to say that, look, suppose the coefficients of let us say in an affine combination are all non-negative, we call such combinations as convex combination, right. So, we call this combination as one convex combination, or it is also called as the weighted average. Right. This is something interesting. So, we see that linear combination. So, in effect what are we trying to say? We say that the linear combination of a set of vectors will give rise to another vector, right. The linear combinations of the vector would give rise to another vector. Suppose if one of the coefficients is suppose let us say we will take this in fact a very valid linear combination. This is, suppose we have let us say alpha 1 is equal to alpha 2 is equal to let us say alpha I minus 1 is equal to 0 and alpha I is equal to 1, and then alpha I plus 1 is equal to etcetera is equal to alpha k is equal to 0, then what we have is the linear combination. The linear combination, let us say alpha 1 u 1 plus alpha 2 u 2 plus etcetera plus alpha I u I plus etcetera plus alpha k u k results in the vector u I. So, which essentially says that I can write the vector any given vector in a set of vectors, I can even write that as a linear combination of the same set of vectors with the coefficients, that particular coefficient being non-zero and rest of equal to 1, and the rest of all the other coefficients can be made 0. So, this is one important stuff that we have. So, we feel we understand that the first thing, linear combinations of vectors results in another vector. Linear combinations of vectors are basically addition of, you add scaled multiples of the vectors, the resultant is going to be a vector, and we see that there are certain special linear combinations that we have, where in which we studied the average of the vectors, and then we looked at the idea of, let us say, affine combination, and in specific in affine combination when the coefficients are all non-negative and then add up to 1, we because it is affine combination, you are again going to say that it is going to add up to 1. So, we are going to say that when the coefficients are non-negative in an affine combination, we end up getting convex combination, right. So, this is what it is. Again, where do we see this linear combination? You see it in lot of places, including the idea of audio mixing and a lot of other things. So, you see a lot of things in examples as linear combinations. Now, the second question is very interesting, and that is what we are trying to we are going to answer now. The second question in the previous class that we had was, look, what would be the strategy that I would adopt in order to study the effect of, let us say, transformation on all the vectors, on the entire vector space. So, what would be the strategy that I would adopt? So, that is a question that we are going to answer now. Okay. So, the question is the following: suppose we want to study the effect of transforming. I mean, this we really do not know what it is to say transform by now, but plain English meaning we know what it is to say transform. We will study linear transformations in the next week. So, effect of transforming or effect of a transformation on, let us take this, what is the effect of a transformation? I would say a linear transformation, but we do not even know what it is. We are just going to say, okay, of a transformation on a vector space. What strategy do we adopt? What strategy do we adopt to study this? This is a question that we want to answer, right. Okay. Now, in order to answer this, we need to study a little bit more about this linear combination of vectors that we just studied a bit back. We want to look at linear combinations of vectors, but with very specific target right now that we are going to do. So, what we are going to do is consider, let us say u1, u2, etc., un to be n component vectors. Right. I want to study u1, u2, un. I have a set of vectors u1, u2, un to be n component vectors. Now, what I want to do is I want to look at this very specifically. I want to look at that linear combination of the u vectors I will call this as u vectors, basically it will correspond to u1, u2, un, that would results in the 0 vector. N component 0 vector. Now, what does that mean? That means my destination is pretty clear. I am not looking for the linear combination which is going to give any random vector as the output. but I want to look at the linear combination of the vectors such that it would result in the 0 vector. I want to look at the right hand side to be the 0 vector. What are the various combinations that can result in the 0 vector on the right hand side if you look at the linear combination of these vectors u1 to u1, right. So, this is what I am going to do right now. So, let us look at this. Suppose we have scalars, okay, let us take this, let alpha 1, alpha 2, etc., alpha n be real scalars. Again I am just going to consider real vectors here, u1, u2, un are all real vectors, that means the components that they have are all real numbers. I am going to look at alpha 1, alpha 2, alpha n to be real scalars. So, the linear combination of u vectors is basically given by the linear combination of the u vectors is given by alpha 1 u1 plus alpha 2 u2 plus etc., plus alpha n un, and on the right hand side I want this 0 vector which is 0 n. I will write it as this, basically I will write this as 0 n, where 0 n corresponds to the n component 0 vector, 0 0 all 0, this is n component. Okay. This is the right hand side that I want with the linear combinations alpha 1 u1 plus alpha 2 u2 plus etc., plus alpha n un. Now, what is interesting is there can be multiple linear combinations which could give us 0. For example, let us say if one of the vectors u1, u2, un is itself a combination of the other vectors, then what you do is you sum all the other vectors and then subtract this particular vector, let us say one of those vectors, you might actually get a 0 vector. Let us see what that is. So, for example, let us take this example. I am going to look at R2 itself, I am going to look at 2 component vectors so that the idea gets driven very clearly. I am going to take u1 to be equal to 2 1 and let us say u2 is equal to 1 2 and let us say u3 is equal to 3 3. These are the u vectors that I have. So, what I want to do is I want to look at the combination which is going to give me the 0 vector on the right hand side. So, what I am going to do is I am going to look at writing the 0 vector as a linear combination of u1, u2, u3, which is basically saying I must be able to write the 0 vector as alpha 1 into 2 1 plus alpha 2 into 1 2 plus alpha 3 into 3 3. We can very clearly see here that 2 1 plus 1 2 if you add you actually get 3 3, which means 1 time 2 1 plus 1 time 1 2 minus 1 time 3 3 gives me the 0 vector. Is this correct? You can also take 2 times 2 1 plus 2 times 1 2 minus 2 times 3 3, that would also give me the 0 vector, right. So, we see that there are multiple combinations in this case, there are multiple possibilities to get the 0 vector by choosing different scalars. Right, by choosing different scalars you actually get the 0 vector, right. In fact, one of the most interesting combination that we have is I can do this also, right. 0 0 I can write this as 0 into 2 1 plus 0 into 1 2 plus 0 into 3 3, even that is a very valid combination which would give me the 0 vector, right. So, we have this one combination wherein which the coefficients are themselves 0, and you also have the other combinations where the coefficients are not 0, but still we end up getting the 0 vector, right. Okay. So, here we are going to bring in the idea of, with this understanding what we do is we bring in the idea of linear dependence. So, we are going to write a new term here, we are going to call linear dependence. Or linearly dependent vectors. When we say linearly dependent vectors, what we are going to say is, suppose we have vectors, suppose u1, u2 etc. un are vectors and alpha 1, alpha 2 etc. alpha n are scalars, not all zeros. So, the scalars are all not all zeros. If okay, scalars, then we will make this statement, scalars then alpha 1 u 1 plus alpha 2 u 2 plus etc. plus alpha n u n is equal to the 0 vector, n component 0 vector is equal to the 0 vector such that not all alpha i's are 0. That means not all the scalars are 0, then we say that u 1, u 2, u n are linearly dependent, u n are linearly dependent. Right. See, the one thing that we have seen is this simply means if you have not all the scalars to be 0 at the same time, it simply means that one of the vectors in the set can be one or more of these vectors in the set can be expressed as a combination of the other vectors, combination of the vectors in the set itself. Then you call this, such set of vectors to be linearly dependent vectors. For example, we just had this 2 1, 1 2 and 3 3. We figured out that the vector 3 3 can be expressed as a linear combination of 2 1 and 1 2, or you can write 2 1 as a linear combination of 1 2 and 3 3, or you can write 1 2 as a linear combination of 3 3 and 2 1. So, when you have this, you see that there is one combination where in which the coefficients are all 0, that linear combination gives me the 0 vector. There are other combinations also that will give rise to 0 vector. So, what we are going to do is we are going to call all those combinations, we are going to set of, if you have a non-zero scalar, set of non-zero scalars such that linear combination of a set of vectors is going to give me the 0 vector, you call such set to be a linearly dependent set of vectors. So, let us write this. So, a set of vectors is said to be linearly dependent, vectors is said to be linearly dependent if for scalars, alpha 1, alpha 2 etc., let us say alpha n, there exists, we will also write this vectors first of all, a set of vectors, we will make this here u 1, u2 etc. un is said to be linearly dependent if for scalars alpha 1 alpha 2 alpha n there exists a linear combination alpha 1 u1 plus etc. plus alpha n un such that not all alpha i's are 0 such that all alpha i's are 0. So, this combination is basically what you call as a linearly dependent set of vectors. So, this set of vectors is called linearly dependent set of vectors. That means, if you have scalars you want to look at the linear combination, then there could be a combination where in which the scalars need not be 0, but then the resultant vector that you get of linear combination to be a 0 vector. Such vectors are called as linearly dependent vectors. So, we will make one important statement here. So, any set that contains any set of vectors that contains the 0 vector is a linearly dependent set, right, is a linearly dependent set. What does that mean? Suppose I have this set S which contains, let us say u1, u2, u3 etc., and then let us say uk, and it also contains the 0 vector. Then I want to get the linear, I want to get the 0 vector as a linear combination of all these guys. So, what I will have, I can write the 0 vector, I will write this as 0 vector to be equal to alpha 1 u1 plus alpha 2 u2 plus etc. plus alpha k uk plus let us say alpha r 0 vector, alpha r into 0 vector. Now, what I can do is I can actually make all the alpha i's 1 to k to be 0 and then make a non-zero combination, make a non-zero value for alpha r, which would still result in a 0 vector. So, I can take alpha 1 is equal to 0, alpha 2 is equal to 0 etc., alpha k is equal to 0, and I can make alpha r to be any real number, is arbitrary. Now, what happens here? We see that the 0 vector has a non-zero combination, what at least there exists one scalar which is non-zero for which you get the 0 vector. That means, this combination is going to be a linearly dependent set. Linearly dependent set ultimately implies that there is a redundancy there. Is this clear? So, linearly dependent set implies redundancy. Linearly dependent set implies redundancy. Okay. Now, we have still not answered the question as to what is the strategy that we need to employ in order to what would you call, in order to study the effect of a transformation on the set of on a vector space or on all the vectors in the vector space. We have still not answered, but we are just towards answering that question. So, what we will do is we will stop at this point and then we will take up, we will proceed with this journey and then try to find out the answer for the strategy that we need to adopt in order to study the effect of a transformation on the entire vector space in the next class. Thank you.